Okay, I wanted to talk today about another application of eigenvalues and eigenvectors and spectral theory in general here. This we're going to apply to something called linear recurrences. Okay, linear recurrences. What is a linear recurrence? Linear recurrence, these are sequences of numbers, often integers and usually integers, in fact, in which terms of the sequence are linear combinations of the previous terms in a fixed way. Okay, at least from some term onward, this is true. Okay, so if our sequence looks like this, x sub 1, x sub 2, x sub 3, right, a sequence, okay? X sub n is a sub 1, x sub n minus 1, plus a sub 2, x sub n minus 2, plus so on and so forth, down to a sub k, x subscript n minus k, and this is going to hold for n is greater than k. Okay, so from the k plus first term onwards, this recurrence will hold. A sub 1, a sub 2 through a sub a are constants. Okay, all right. This would be an example of a linear recurrence, or this is the general. That's not really an example. This is saying what happens in general. Okay. All right, let's be very concrete. Let's take a really concrete example or two here. Okay, probably the most famous recurrence is the Fibonacci sequence that you've probably seen before. Let's talk about some of the terms of the Fibonacci sequence. They are 1, 1, 2, 3, 5, 8, 13, 21, 34. What's the next term? The next term is 55, yes. Do you see how to get the Fibonacci sequence? What it turns out is every term in the sequence after the second one is the sum of the previous two. Okay? It's going to be the sum of the previous two. So 2 is actually the sum of 1 and 1. 3 is the sum of the previous two, so that's 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5, and so forth. Okay? Let's talk about, some people might call this initial conditions here. My first two terms of the sequence are given. They are 1 and 1. So x sub 1 is 1, x sub 2 is 1. Okay? And then the nth term of the sequence is x sub n minus 1 plus x subscript n minus 2. Do you see if this is the nth term of the sequence, which we're representing as usual when we're talking about sequences with subscripts, then the previous term would be what? X subscript n minus 1, and the term previous to that would be x subscript n minus 2. Now this is going to hold whenever n is greater than 2, okay? Alrighty? Now here's our little goal here. We want a formula for x sub n, an explicit formula that for the nth term of this sequence that does not require us to actually compute all the previous terms. So if I was interested in the 100th term of this sequence, I would like to be able to compute that directly without computing all the previous 99 terms. Okay, alrighty, I'm going to show you that we can do that using spectral theory here. Okay, now there's going to be actual shortcuts when people start working with linear recurrences to what we're going to do, but it's based upon what we're doing here. Okay, so you can actually take some shortcuts later. Okay, but I'm not going to teach you those. Okay, wait for a combinatorics class if you want that. Well, maybe I'll mention them later though. Okay, anyways, the recursive formula, or recursion so-called, can be written, this is the recursion, this thing, the recursive formula. Okay, and these are initial conditions over here. Okay, this is how you start out, in other words, initially. But this is what we call the recursion. Now, this is a two-element recursion, or okay, two-term recursion. Okay, see how the nth term is determined by what? The previous two terms. The previous two terms. If I had, I'm going to show you a three-term recurrence here. That's in terms of the previous three terms. Okay. Here we're just dealing with the previous two terms. So what I'm going to do is when I write this in vector matrix form, this recursion, I'm only going to take two terms because it's a two-term recurrence. If there were if it was a three-term recurrence, I would have x sub n here, x sub n minus 1, and then x sub n minus 2. Okay? Alrighty? Alright, anyway, let's talk about this. I'm going to create a little vector here. This is the nth term of the sequence and the previous one. Okay, so you see I've written there x sub n, and after that the next entry, x subscript n minus 1. Okay, now wait a minute. X sub n is actually x sub n minus 1 plus x sub n minus 2. Okay, so I've got x sub n in terms of n minus 1, n minus 2. How about x sub n? X sub n minus 1 is just x sub n minus 1. Okay, I think we can agree with that. All right, so look good. Now I'm going to just show you here that we can actually write that as a matrix product. This is 1, 1, 1, 0 times this vector, x sub n minus 1, x sub n minus 2. Now, let me just mention here, let me maybe jump down here for just for a second here. Now I'll just go on here. Okay, and then we'll discuss this again. All right. I'm going to call v sub 1 x sub 2, x sub 1. Okay, so this is sort of my initial vector. That's why I'm using subscript 1 on this guy. If you wanted to use a different subscript like v sub 2, that would be possible. But the way I've done it, I've made it so what? The subscript on my vector v matches the subscript on the second term in the vector, the second entry, the subscript of the second entry in the vector. Okay, we know that's going to be what? X sub 2, x sub 1, that's 1, 1, remember? Okay, those are our two initial values for the Fibonacci sequence. Okay, I'm calling that vector v sub 1. Okay, v sub n minus 1 would be what? X sub n minus 1, x sub n, reading upwards this time. See how these match here? Okay, this is going to have these match. Okay, and then what? This guy right here, this subscript is 1 more than this guy. Okay, so this would be consistent with what? If I let n equal 2 here, then I would have v subscript 2 minus 1, or v sub 1 is x sub 2, x sub 1, just like I have above. Okay, what would v subscript n minus 2 be? That would be what? Reading up this time, x subscript n minus 2, and then the one right after that. So that would be x subscript n minus 1. Okay? Do you see how that works here? All right. Now, how could I rewrite this recursion above, the matrix form of the recursion? Okay. Do you see on this side, I really have what? I'm calling that v sub n minus 1. And on this side, I've got this matrix A, which is 1, 1, 1, 0. Okay. So I've got that. I'm calling that A. And then this is actually what? V sub n minus 2. So our recursion is written this way now as a matrix product. I'm going to believe it or not, this is going to be helpful. Okay? So do you see how that works? That's just a rewriting of this matrix vector equation above. Okay? Now, once you get the idea here, before I use this really formally here, just think about this. V sub 2 should be what? A times V sub 1, right? The previous vector. V sub 3 should be A times the previous vector, so that's V sub 2. But V sub 2 from the previous equation is A times V sub 1. So V sub 3 is actually what? A squared times V sub 1. What would V sub 4 be? That would be A times V sub 3. So that would be what? Using this formula up here, that would be A cubed times V sub 1. What would V sub n be? Okay, V sub n would be what? A to the n minus 1 power. You can see the pattern forming here. It would be A to the n minus 1 power times V sub 1. By the way, if you did not want to go to, see, I'm just using V sub n here because I like it, okay, because it's better. But if you didn't like that and you wanted to write it with V subscript n minus 1 like we have up there, you could certainly do that. But then your power up here would still be 1 less than the subscript. And up here you would have what? N minus 2 instead of n minus 1. But you could certainly do it that way, okay? But the way I've done it here, just to show you here, I've got v sub n being what? A to the n minus 1 times v sub 1. Okay, just generalizing what we discovered up there. What would v subscript n be? Well, again, notice how we construct our v's here. That would be v subscript n on the bottom, and what? The subscript on the top entry would be v subscript 1 more than that, so n plus 1. Okay, a to the n minus 1. What was v1 again? Let's be explicit. That was 1, 1. Okay, so here is our formula. Now, you notice here that we've got what? We've got a square matrix that we're raising to a power, and you should know we have shortcuts for doing things like that in the case that the matrix A has a diagonal form. In fact, we're going to show that it does. Okay, so it has a diagonal form. Let's do that on the next page here. Okay. Okay, by the way, I'm trying to get this, so I'm going to be grabbing that bottom entry, right? The x sub n. That's what I wanted a formula for. Okay, anyways, let's keep going. All right, to find a diagonal form, what do we have to do? Let's find the characteristic equation of our matrix A. So I'm writing it this way. You know, there's a couple ways we do it, but it's going determinant xi minus A. Okay, so that would be this determinant. Vertical bars, x minus 1, negative 1, negative 1x. Okay, that's because A up here. Let's look at A. Here's A again, right? Okay, so if I went xi minus A, it would be x minus 1, negative 1, reading across, negative 1, x minus 0, or x. Okay, now just take the determinant of that, okay, the matrix on the inside, and we would actually get this x squared minus x, and then subtract the product of the off-diagonal elements, that's 1. So I'm subtracting 1. So the characteristic polynomial is x squared minus x minus 1. Now what do we want to do with that to find eigenvalues? We want to set that thing to 0 and solve. So go x squared minus x minus 1 equals 0. You won't be able to factor that in the integers. You're going to have to go to the quadratic formula, and you're going to get these. You're going to get 1 plus or minus the square root of 5 over 2. Okay, so I'm going to say lambda 1 is 1 plus the square root of 5 over 2. So that'll be the first eigenvalue. Okay, all right. Now I'm going to do the following here. Remember, up here, I'm going to come up here. Remember, this thing is being set to 0 for the various values of x, which I'm calling lambdas here. It's being set to 0. So you're going to solve. You're going to go 1 plus the square root of 5 over 2 minus 1, which is actually negative 1 plus the square root of 5 over 2. Okay, so that's where that came from. So that's our lambda minus 1. And then I've got what? Negative 1 here. Okay, and then I've got negative 1 here. And then I've got my actual x value, or lambda, right there. Okay, now we know this is going to just have what? It's not going to be of rank 2. It's only going to be of rank 1, right? Because this is going to be an eigenvalue here. So it's easiest to actually, when you get it into row-reduced echelon form, it actually ends up looking at the second row is where it's at here. And it turns out it has this form, 1 and then negative of 1 plus the square root of 5 over 2, 0. And then the bottom row is all zeros here. Can you see an eigenvector for this? Okay, it should be easy. It actually turns out it's our lambda and then 1. Okay? Now, let me throw this in while I'm here. This value, 1 plus the square root of 5 over 2, is sometimes given this designation, phi. Okay, that's the Greek letter phi. It's sometimes called the golden ratio. Okay, the golden ratio, phi. 1 plus the square root of 5 over 2. So I'm going to write it this way. I'm going to go phi 1. Okay? All right, what's our other eigenvalue? It was 1 minus the square root of 5 over 2. Now I do the same thing with it that I did up here. Okay? All right? And we get a very similar result here. Okay, in the end, because of this second row here, the negative 1 and then the x value, or the lambda, negative 1 and then lambda here. This is just arithmetic up here. You can go through that. subtracting 1 from lambda. But this is really where it's at here. So what you get is just like before, 1 and then negative of the lambda right there in the row-reduced echelon form. So once again, we get an eigenvector in which we just have our lambda value and then 1. Now, I'm going to write that as phi with a bar over it, okay, and then 1. Phi with a bar over it is 1 minus the square root of 5 over 2. That's also, by the way, I would like you to think about this. It's really easy. Think of 1 being 2 over 2. Phi bar is actually 1 minus phi, by the way, okay? When I write phi bar, I sometimes write conjugate to phi. This is not the regular conjugate you think of in terms of the complex numbers where you're going a plus bi conjugated is a minus bi. This is more like this. If I've got integers a plus the square root of 5 times, let me put the b in front, b times the square root of 5 instead of the square root of negative 1, and I take its conjugate, I change the sign on the irrational part. It becomes 1 minus b times the square root of 5. Okay? I'm telling you more than you really need to know, but so they are conjugates in another way, something you guys probably haven't studied yet. Okay, certain fields we call them. Okay, anyway, doesn't matter. All right, so this is just my designation. You could just think of it that way. What's our p going to be? Remember, we're trying to find a diagonal form. We'll take those eigenvectors and let's stack them, in here and make a matrix out of them. So we've got the first eigenvector being phi 1 and the second eigenvector being phi bar, or conjugate of phi 1. Okay, compute p inverse. Okay, it's very easy to do with our determinant formula. Okay, this is what it partially is. Okay, let's be maybe a little more explicit. Here's our p. Okay, so I've got the golden ratio 1, the conjugate of the golden ratio 1. P inverse, the difference of these two turns out to be the square root of 5. So that's 1 over the square root of 5. 1, negative 1, reading down. Okay, this is negative phi bar. Okay, and then phi. By the way, negative phi bar from this formula right up here is actually phi minus 1 here. So we could also write p inverse this way. Okay, alrighty, and there we go. All right. All right. Sorry for the interruption. It gave you a chance to think about that. Okay, anyway. So we're looking diagonal form, right? So P inverse AP should be D. That means A is P, D, P inverse. Okay, what's our D? These is what? The eigenvalues down the main diagonal. Okay, in the right order here. All right. So if I'm going A to the n minus 1 power, that's P times D to the n minus 1 times P inverse. Okay, just put those in there. Okay. D to the n minus 1 power is going to be phi to the n minus 1, 0, 0, phi bar to the n minus 1. And then remember we have our P inverse over here. Okay, 1 over the square root of 5, 1, negative 1, phi minus 1, phi, reading down. Okay, let's come back here. We remember this formula. Okay, so I'm going to take that and I'm going to multiply it on the right by 1, 1. Okay, all right. And then we'll start working out the details. Let's multiply these two together first. And you get phi minus 1, so that's really phi bar here. Okay, multiply it on here. Okay, and you get phi to the n. Okay, this is actually ends up being negative phi bar right here. So that in the end we get negative phi bar to the n, phi to the n, and that's being multiplied on what? The matrix P. I factored out the 1 over the square root of 5, by the way, here. Okay, that came out. Okay, all right. Now all I did was pick off what? You remember, I'm just looking for this guy. I'm not looking for the formula for the n plus first value. I can get that from the formula for the nth value by letting n equal n plus 1, right? Okay, I'm just looking at the bottom here, the bottom entry. So do you see here when I multiply this by this, okay, and don't forget your 1 over the square root of 5, that you end up getting this. So the nth term of the Fibonacci sequence is 1 over the square root of 5 times phi to the n minus phi bar to the n, okay? Or if you want to be really explicit about it and write what phi and phi bar are equal to, then you end up with this, okay? Alrighty, all right. So now if you, what did I say, the 100th value of the Fibonacci sequence, you could actually do that, just let what? N be 100, and use your calculator on this, and you can see you don't need to know all those previous terms. Okay, alrighty. Let's try another one. Let's do this example 2 here. Okay, so I've got a sequence that's starting out like this. You can see from the initial conditions, 0, 1, 1. Okay, now you can see with my k is equal to, the way I originally wrote it, you can see my k is equal to 3 here. So I need to know what? 3 previous values, the immediate 3 previous values, to know what the nth value is, right? But they're related this way. Okay, so x sub n is 2 times x sub n minus 1 plus x sub n minus 2 times x sub n minus 3. Initial conditions 0, 1, 1. Now, because it's a 3-term sequence, I'm going to be doing this. I'm going to go x sub n minus 1, x sub n minus 2. So we've got what? 1, 2, 3 terms here. Okay? Now, what would be, imagine this is a matrix, or as the vector with what is a function of n. Replace n by n minus 1 everywhere, and you've got this previous vector here, okay? And then you've got this relationship between those two vectors. This vector is this matrix, this 3 by 3 matrix, which I will just designate it once again as A here, okay, times what would correspond to the previous vector, or the vector associated with n minus 1. Okay, well, what am I going to do? I'm going to find a diagonal form for that A. Okay, so I find its characteristic equation this way. Okay, all right, just like we did before, only it's a 3 by 3. And I work out the details on this one, and this one is particularly nice here. I went ahead and thought about expanding down the first column, okay, and doing a little factoring. Turns out we want to set that to 0, right? It turns out it factors very neatly, x plus 1 times x minus 1 times x minus 2. And then I'm going to set that to 0. Okay. Okay, so I've got c a sub x set to 0, essentially. Okay, and then I've got the following 3 eigenvalues. Lambda 1 is negative 1, sorry. Lambda 2 is 1. Lambda 3 is 2. Okay, and then I need its diagonal form, right? Okay. All right, I've got to find eigenvectors associated with each one of these eigenvalues. Okay, this, by the way, is where we can get some shortcuts. You don't actually have to go through this entire procedure to get a formula for x sub n, but that's something you can study in combinatorics. Again, I've mentioned it, but I'm not going to go into detail of that. Let's practice this instead. Okay. Once again, remember, we're coming up here and we're treating this as an augmented system. I'm letting x take on the various eigenvalues and setting it to 0, right? Okay, so that's what I'm doing. I'm setting it to 0, so you can see it as an augmented system. When lambda is equal to negative 1, I get negative 3, negative 1, 2 is set to 0, negative 1, 0 is set to 0, 0, negative 1 is set to 0. Okay, here's the row-reduced echelon form. Okay, and you can easily figure out an eigenvector for this. An easy eigenvector I found was 1, negative 1, 1. Okay, alrighty, let's go to the next one where lambda is equal to 1. And we get this system, negative 1, 2 is set to 0, negative 1, 1, 0 is set to 0, 0, negative 1, 1 is set to 0. This has this row-reduced echelon form here. Okay. Easy to solve here. It's easy to find an eigenvector, 1, 1, 1. Okay, so I called that W2. Finally, my last eigenvalue here is 2. This corresponds to the following. Okay, system 0, -1, 2, 0, -1, 2, 0, 0, 0, -1, 2, 0, just like the top here. This row reduces to the following. 1, 0, -4, 0, 0, 1, -2, 0, zeros all along the bottom. What's an eigenvector corresponding to this? It turns out to be 4, 2, 1. All right, so I stack those as columns into the matrix, forming P. I find its inverse. I factored out 1/6 for convenience here. So P inverse, I actually use my calculator for that. Okay. Now, A should be what? Now, that's our original matrix in the recursion. Okay. So A should be what? P times what? The diagonal vector D, or diagonal matrix D, formed from the corresponding eigenvalues down the main diagonal. And there's P inverse. And so there we have it. Okay, so there's our D. Okay. Now here, I started out this way. You know, there's, again, remember our subscript in the beginning. I called it my initial vector was, I'm using 1 since it's the initial one. But it actually corresponds to what? x2, x1, x0. That was what? Remember the initial conditions were 1, 1, 0. Okay. V sub 2 would be what? X sub 3, X sub 2, X sub 1. Notice that the subscripts match on what? They always match with the second entry this time with a subscript on the vector V. Okay? And you can go through just like we did before. What's that doing there? I don't know what that is. But anyways, this is what we have here. Should really box that in too. We've got this. Okay? So I'm really looking for the middle entry on V subscript n. Okay? All right, so let's go ahead and do this. Let's run through this thing. And if you start taking powers on this, and here's our P, here's our powers on D. Okay? This was really 1 to the n minus 1, but that's just 1, so I just left it. Okay? And then I put those in there. Okay, and did this, and the rest is just basically a raw calculation. It's going through all the details on this thing, so I'll let you look at that. Okay, so just multiplying these all together. Okay, now what I'm interested in is what the middle entry in this. Okay, so I've been multiplying from the right all the way through, and ultimately this is what I found for the middle term. Okay, that you get this, which is ultimately the following, conveniently written 2 to the nth minus -1 to the nth, all over 3. Okay, so now we have a formula for the nth term of the sequence without calculating all the previous terms. Okay, well, I hope you understood that. Okay, you should be able to tackle those problems then.